Alright, this is 5B notes. Our unit 5 is going to be talking about polynomials, and we're going to start today by looking at some vocabulary dealing with polynomial functions. So first of all, let's define what is a polynomial function. It's a function in the following form, where a sub n, it can't be 0, but a sub n, which is the coefficient, all of these are just coefficients, have to be real numbers. So the coefficients are real numbers, and my n1, all right, those are my exponents. My exponents have to be whole numbers. So far we've dealt with two types of polynomial functions. Back in Algebra 1 you did linear, which has a degree of 1. Highest exponent is 1. And we've done quadratics, which has a degree of 2. So the degree of a function is the highest exponent. The degree will determine the end behavior and the maximum number of solutions of the polynomial. Now the following theorem, and we're going to put this in application here in a little bit, says if f of x is a polynomial of degree n, which is greater than 0, then the function f of x equals 0, the zeros, this will have exactly n solutions provided repeats are counted as multiples. And I'll show you an example of this in a little bit. Okay? Alright, so first of all, let's go through and you need to be able to tell whether something is a polynomial function or not. So we're going to look at that definition. If it is a polynomial function, we're going to rewrite it in standard form and state the degree, because that's going to tell me how many solutions I've got. Alright, so look at this. Look at all your coefficients. -5, 3, and -1. They're all real numbers. They're actually integers. Alright, so the first condition is met. Now your exponents, 2, 4, they're whole numbers. Okay, whole numbers. And so this is a polynomial function, yes. Now to write it in standard form, you put the highest exponent first. You do it by the exponent, not the coefficients. So this is in standard form. Since the highest exponent is 4, this has degree of 4. This means this has 4 solutions. It has a maximum of 4 solutions. Alright, look at the second one. Pi is still a real number. Alright, and 2, that's a whole number, so this is yes again. It's already in standard form, so the highest exponent is 2. Alright, number 3. Alright, coefficients. Square root of -2. That's imaginary, so it's not real, so this is not a polynomial function. Okay? Alright, let's look at more vocabulary. So a polynomial function, notice we have more curves now, okay? So this thing can curve a number of times. And eventually we're going to learn how to graph these polynomial functions. We've got to learn some stuff first. So we're going to answer the following information about this. All right, here's where that theorem comes in. Because this touches the x-axis 1, this is called a double root when it bounces off like this. And we count that twice. So the least degree here is 1, 2, 3. So my least degree is 3. So I know it's the smallest degree it can be is a third degree. Alright, we can have imaginary solutions and I can't see those because they're not touching the x-axis. Alright, lead coefficient. Since the right hand side of this graph is going up, that means my lead coefficient, my A, is positive. Okay? Alright, the zeros. Where does it touch the x-axis? Well, it touches at -1. And since we're counting 3 as a double root because it bounces off at 3, we're going to write 3 twice. Because that's going to come into play when we write our factors. Alright, so our factors. If x is equal to -1, then x plus 1 is a factor. And because we have a double root here, this is going to be x minus 3 squared. Before we answer the y-intercept question, let's jump over and look at the equations. I don't want you just relying on your graph now. We are going to have equations, so I want you to make sure you're checking that y-intercept mathematically. Alright, so starting off right now, I'm going to tell you what A is. Later on in the unit, you're going to be finding that A. But right now, I'm telling you A is 1. So we're going to multiply the factors times themselves. All right. You can leave it like this right now. Later on here again, when you learn more, we're going to be turning this into standard form. You're going to be multiplying it out. All right, to find the y-intercept, that's when x is equal to 0. So we're going to plug 0 in for all of my x's. So when you solve that, you're going to get 9. So your y-intercept is 0, 9. All right, let's look at increasing and decreasing intervals. All right, right now, how we find a local maximum and minimum, the reason I call it a local because it's the highest at that particular point. It's the highest part of this graph, and this is a local minimum. I just used the calculator. This one is going to be 3, 0. We can read that off our graph. Okay. When you get to calculus, you're going to learn how to find the local maximum ends, but that's beyond the scope of our course. So we're going to use the calculator right now. So remember, when we do increasing intervals, we're only interested in our x, and we're going to move from left to right on this graph. So negative infinity, so this going up, so that's positive, negative, and then positive again. Okay, so remember, intervals are always open when they're increasing and decreasing. So from negative infinity to 1/3, and then from 3 to infinity is my increasing intervals. And then my decreasing intervals from 1/3 to 3 is my decreasing interval. All right, in behavior, as x approaches negative infinity, my y is going down, so it's approaching negative infinity. And as x approaches positive infinity, my x is going up, so it's approaching positive infinity. All right, notice this is an odd degree. Anytime you have an odd degree, the end behaviors go in opposite directions. And we're going to look more at that here in just a moment. So you need to be able to tell me about the end behavior. So before we're going to complete the following and what's on the back here, but you need to look at these examples. So in group 1, what do all of these have in common? Look at the degrees. They all have what kind of degrees? Well, if you said even, you get 2, 4, and 8. They're all even degrees. Well, I don't know what all of these have in common. All right, how about your lead coefficient? They all have 1, 1, and 2. They're all positive lead coefficients. So A is greater than 0 or positive. So what do you notice about the end behavior? All right, they're going in the same direction, and they're both going up. So let's go to our, flip over a little bit, and let's do that first one. If the degree is even and A is positive, then as x approaches negative infinity, y is going up, so it's approaching positive infinity. And as x approaches positive infinity, f of x is still going up, so it's approaching positive infinity. So A, degree even, A is positive, they're both up, up. All right, let's go back and look at group 2. What do they have in common? Degree, 6, 2, and 12, they all have even degrees. So that tells us we're going in the same direction. Now, what direction? Look at your A's. -1, -4, and -1. So here A is negative, they're less than 0. Okay, notice they're both going down. So if it's even and A is positive, they both go up. If A is negative, they're both going down. So let's go fill that out on our chart. So here we're both approaching negative infinity. Okay, so even, you got to remember they go in the same direction, and what A is, positive or negative terms, it goes up or down. All right, let's go back and look at groups 3 and 4. All right, what is group 3? All the degrees in group 3. 3, 5, and 7, so they're all odd degrees. All right, A is, in this case, they're all 1. All right, so A is greater than 0, so it's positive. All right, I already said that when you have odd degrees, they go in opposite direction. And if A is positive, the right-hand side's always up. So if the right-hand side's up in an odd degree, our left-hand side is down. All right, odd opposite, OO, odd opposite. All right, so let's fill that in. So as x approaches negative infinity, f of x is going down. And as x approaches positive infinity, f of x is going up, so positive infinity. So that just leaves us one more. All right, what do all of these have in common? Well, they're all odd degrees. But this time, A is negative. A is less than 0. All right, what's happening? Instead of the right-hand side going up, the right-hand side's going down, which makes the left-hand side go up, because odd is opposite. So let's summarize that. So as x approaches negative infinity, f of x is going up, positive infinity, and as x approaches positive infinity, f of x is going down. So here, all right, easy way to remember this is the right-hand side is up. No matter what graph, your a is positive. Now you got to do even or odd if the left-hand side is going to follow suit if it's even, or go the opposite way if it's odd. And here again, this is going to come into play later on when it's going to help us graph these polynomial functions. All right, from 5a, hopefully you recognize that new parent point pattern. These are called cubics. Okay, so we're adding another set of parent points. So there's parent point pattern that you need to memorize. X or y is x cubed. We're cubing. All right, so it's that following pattern are going to exist for any cubic. Now, like with all of our graphs, a, h, and k are going to always do the same thing they did when we did it with quadratics, when we did it with linear, and when we use the transformations for absolute values. Here my a is 1, my h is negative 1, and my k is negative 2. Alright, so we're going to start counting from negative 1, negative 2. It's no longer called a vertex, but it's where we're going to start counting from. So graph negative 1, negative 2, and we're going to start counting our parent points from there. So we're going to go left 2, down 8, left 1, down 1, 0, 0, right 1, up 1, and right 2, up 8. Alright, make sure this is a curve, so don't zigzag this. Make sure you have nice curves and put your arrows on the end. That's our cubic graph. Okay, let's look at another one. Alright, so a here is negative 1/2, h is 2, and k is 1. So we're going to start counting from 2, 1. Alright, let's do our pattern. But this time we're going to multiply, because a is negative 1/2, we're going to multiply all those y values by negative 1/2. So what do we get? We get positive 4, positive 1/2, 0, negative 1/2, and negative 4. Alright, so plot our point, 2, 1, and we're going to start counting from there. That's a lunch bell, got me. Alright, start counting from there. I'm going to go left 2, up 4. I'm going to go left 1, up 1/2, 0, 0, right 1, down 1/2, and right 2, down 4. Alright, here again, this is a curve. Try to hit the points better than I did. So curving that through there. Alright, there we go. Alright, more points would fit, I don't think, because our next point is 327, so we're not going to be able to fit the next point on there. But this pattern does continue, because these are continuous graphs. Alright, so make sure you, like I said, memorize that parent, that new cubic parent pattern, parent points. You're also going to need to go backwards. So given the equation, we're going to go backwards and find the, given the graph of the equation, we're going to go back and find the equation. Here you need to memorize the general form of a cubic is the following. Alright, so that means we need to find A, H, and K. Alright, this turnover point, that's going to give me my H and my K. So this is right 2, up 1. Alright, let's find the A. I'm going to show you two different methods, just like we did this with the quadratics. I'm going to use my parent point method. Alright, I need another point on my graph. I'm going to use this one. I could use either one. It doesn't matter. I'll show you, we get the same answer either way. Alright, what should the parent point be? This goes right 1. Right 1 should go up 1, but what's actually happening? Right 1 is going down 1. So to find A, you're going to put the new over the old, so A is equal to negative 1. Now it's just a matter of plugging and chugging and to get our final answer. So the opposite or negative x minus 2 cubed plus 1. There's the equation of my line. Alright, please don't leave off that cube because if There'll be a line if you left off the cube. So be careful. All right, let's look at the other method, the algebraic method. Now you're going to have to use the algebraic method later on when we start doing this with polynomials. All right, here again, write down your general form. This will force you to memorize it. Don't leave off that cube. All right, find your kind of your turnover point. My h and k. I still need to find my a, my h, and my k. I'm just going to do this algebraically. All right, so I went left 3, so that's negative 3 for h, and down 2, that's negative 2. I need another point on my graph, so let's use this one. That's the only other whole point. I could use this one too. All right. All right, the coordinates of this one is what? Negative 2, 0. So this is x and y. So we're just going to plug in everything we know and find what we don't know, which is in this case a. So 0 is equal to a times negative 2 minus a negative 3 cubed minus 2. All right, we're solving for a. So let's move the 2 over. And let's clean up what's in these parentheses. This becomes plus, which 1 cubed is 1. So 2 is equal to 1a. So a is equal to 2. So a is 2. So make your equation. Don't forget your y equals or f of x equals. So you have 2x minus a negative, which makes it plus 3 cubed minus 2. So there's the equation of my cubic function. All right, if you have any questions, please make notes or remember to ask them in class.